Hello, and welcome back to a new video. We're going to be starting a series on tensor calculus. This will be the Cartesian tensor calculus of Euclidean metric spaces. In this part, we're going to introduce mathematical spaces. There's a couple of prerequisites that you should have down before engaging with this video, but if you don't have these down, you may still find this to be of interest. In this series on Cartesian tensor calculus, it will be assumed that you have basic familiarity with multivariable calculus and linear algebra. The following notation and operators should of course be familiar to you. We have differentials, dx, dy, dz, and then differential area elements such as dA and differential volume elements such as dV, etc. You should also be familiar with basic derivatives such as dy by dx, which is the derivative of y in respect to x, or a derivative of a function in respect to y, or a second derivative such as the second derivative of u in respect to v. And then you should also understand notation such as f prime of x, which is another way of saying dy by dx, or the second derivative, such as f double prime of y, which would be the second derivative of x in respect to y, etc. You should also be familiar with partial derivatives from multivariable calculus, such as the partial derivative of y in respect to x, partial z in respect to y, or the nth partial derivative of y in respect to x, and then of course mixed partial derivatives such as d2f in respect to x and y, and then we have del sub x, which is another way of saying the derivative in respect to x as an operator, etc. You should be familiar with concepts of gradient, divergence, and curl, which are given by these three operations listed. You should know a bit about integration, such as the integral, in this case an indefinite integral of some function f of x in respect to x, that's one example. You should also understand a bit about definite integrals, such as an integral ranging from a to some constant or function b of f of x dx. And then multi-integrals, such as the triple integral over the reals, which would be ranging from negative infinity to infinity of some function, say f of x, y, and z, dx, dy, dz. This could be written this differential 3 form here at the end can be written as a differential volume element dv, etc. And then based on any knowledge of calculus, you should of course understand the concept of a limit, such as the limit of some function f of x as x approaches c equals the evaluation of the limit itself. Some concepts from linear algebra should also of course be familiar to you, as I mentioned, and a few of these will be listed here. You should have an understanding of what a vector is, what are basis vectors and eigenfunctions. And of course, many times in this series, we might write out a vector, but we may not write the arrow notation. But in those cases, it will be implied that we're working with vectors. So you have this x vector, and then you have a basis vector x hat, or v sub x, which shows you a component of a vector. And then you have what's called the eigenvalue equation, a times v equals lambda v, where A is some type of arbitrary matrix acting on some vector v, and that equals what's called the eigenvalue acting on v. You should understand basic matrices such as ABCD, this 2 by 2 matrix, or in the highest, most advanced concept of a matrix will really be in a three-dimensional case. So we'll call this matrix A, B, C, D, E, F, G, H, I. And then we have a 3 by 3 identity matrix. These should all be familiar to you. The idea of a dot product and cross product should be familiar with you, such as A dot B or A cross B. The idea of a trace and determinant should be familiar with you, such as the trace of A, which in the case of the matrix listed as A, that's just going to be the sum of the diagonal elements. So the trace of A in this case would be A plus E plus I. And then you have the concept of a determinant of B. So let's say that the matrix B is equal to this 2 by 2 matrix ABCD, then the determinant would be A times D minus B times C. The idea of a matrix inverse, the idea that such a thing exists, should be familiar to you. So if you have some inverse of a matrix A to the power of -1, we really won't call that, we'll just call that A inverse. We'll rarely ever say to the negative first power. if you take some matrix A and act upon its inverse, you should get back the identity matrix or identity element of that matrix. And then, of course, you should understand basic sigma notation, such as a discrete sum from n equals 0 to some big N of a function f of x. So let's say you have some polynomial where n is a positive integer, and that polynomial, that variable will be x to the n, for example. This would be x to the x to the 0th power, which is always 1, plus x to the first power, plus x to the second power, up to some larger integer n. So first we'll ask the question, what is a mathematical space? A space is a structured set that establishes the notion of relationships between arbitrary points. Examples of spaces we will rely upon in this series are given by the following. We'll go over what topological spaces are. In this video, we'll also go over what metric spaces are. Then we'll go on to cover vector spaces, and then Banach spaces, Euclidean spaces, and then we'll wrap this up in a concept called manifolds. And here's a little graph or a picture showing you the relation of the most fundamental spaces, many of which we will see in this video series. So I'll give you a little bit of time to look at that. Of course, you can pause the video if you want to take more time to see the relationships between these fundamental spaces. So first, we'll cover topological spaces, since that's the most general space in our study. Topological spaces are yielded when we impose upon a set the notion of quote-unquote closeness. Closeness is yielded by the idea that there exists an arbitrary notion in which two sets or elements within a set are near one another. For the applications for which we wish to be more specific, such as in this series, this alone does not give us enough information to define a quote-unquote distance between these sets or elements. However, it provides the groundwork for which the other spaces may emerge when a topological space is endowed with additional structure. In essence, this is the most general mathematical space that exists for which we may define the concepts of limits, closeness, and continuity, and it's closely linked with the study of calculus or analysis. Without a topological space, mathematical analysis simply does not exist. To give additional structure for which we can obtain a notion of this distance idea, we rely upon something called a metric space. So what are metric spaces? A metric space is a topological space, which we just discussed, that's endowed with the notion of distance between elements of a set. So let's gain an idea of what that means. The distance between points of a space is given by a function called a metric. When we learn later more about metrics, we will refer to them in our case as metric tensors, where tensors generalize the notions of scalars, vectors, matrices, etc. Let some small g be the representation of a metric, and capital A be an arbitrary set of your liking. A metric space is a function A and G with the following map. So G maps the product of A and A to the real numbers. Let's bring that up here so we can continue looking at this map. This function, and yes, it is a function represented as a map, must satisfy the following four axioms. 1. The distance from an element to itself is always 0. This seems kind of common sense. We can write this as an equation by the following. So g of x with itself equals 0. 2. The distance between two separate points, we'll call them x and y, must always be positive. so g of x and y is greater than 0. 3, the distance from x to y is symmetric with the distance from y to x, so g of x and y is equal to g of y and x. And then 4, the triangle inequality must hold, which I will explain in simple terms. So say we have 3 variables x, y, and z on a Cartesian or Euclidean plane, or I guess in this case it would be a 3-dimensional space. The distance from x to z must be less than or equal to the sum of the distance from x to y plus the distance from y to x. The 2 most common metrics many people are familiar with are the following. 1, distance on the real number line. So we have a metric composed on a and b, and that just is given by the absolute value of a minus b, a very basic definition of distance, at least in terms of a real number line. 2, distance on a 2-dimensional plane. So we see that g of x and y is given by the square root of the sum of the squares of x sub 1 minus y sub 1 and x sub 2 minus y sub 2. This can be calculated and proven, of course, using the Pythagorean theorem, and in fact it's hidden within that equation in disguise. So x squared plus y squared gives some distance r squared. This, of course, can be generalized to higher dimensions. So now we're getting more specific. We want to consider vector spaces. Hinted at near the end of our discussion of metric spaces was part of what makes up a vector space. When our set is endowed with linear combinations, we can impose the ideas of addition and multiplication upon these combinations. In many cases, their inverse operations appear for free. These ideas, when imposed on the space itself, yields what's called a vector space. We will consider the fundamental axioms of a vector space on the next slide. There are 8 axioms that compose what's called a vector space. Number 1, vector addition is associative, so x plus the quantity y plus z is equal to the quantity of x plus y added to z. 2, vector addition is commutative, so it doesn't matter which way we add them, they are equivalent, so x plus y equals y plus x. Number 3, there exists an additive identity called 0, so adding 0 to any scalar or vector gives back that same vector or scalar. Number 4, there exists an additive inverse, such that, for example, x plus negative x gives back 0. This is the same thing as defining subtraction. Number 5, there exists scalar multiplication. So a scalar multiplied into a quantity of a scalar multiplied by a vector is equal to the quantity of those scalars multiplied together acting on the vector. Number 6, there exists a multiplicative identity, and that multiplicative identity is called 1. Multiplying it into any vector or scalar gives back the same vector or scalar. Number 7, the scalar distributive rule. So we have a scalar a multiplied into the quantity of vectors x plus y is equal to a times x plus a times y. Number 8, the vector distributive rule. We multiply a vector into these scalars a plus b, we get a times x plus b times x. Since scalars, derivatives, integrals, etc. satisfy these axioms, they too are all examples of vectors. Indeed, even a real number is a vector. And wait for it, so too are matrices. Let's consider now Banach spaces. We want to add additional structure to a vector space that will make it a complete space with the notion of distance enforced upon it. To do this, we endow our vector space with a metric, establishing a complete quote-unquote normed vector space. We can impose a metric norm with the following limit condition on the vector space. So we have the limit as n approaches infinity of the norm of x sub n minus x always equals 0. This creates a quote-unquote Cauchy complete space. This means that every element of a sequence of the space becomes arbitrarily closer to one another as the sequence progresses. So for a complete metric space, we'll call it capital X and G. The above equation can be written as the following. The limit as n approaches infinity of x sub n is equal to x in this complete metric space. So with this in mind, we can define a Banach space as a complete vector space endowed with a metric. Now we're going to get a little bit more interesting with Euclidean spaces. We can now consider the space of interest for our study of Cartesian tensor calculus within this series. A Euclidean space in n dimensions is denoted by r to the n, where r is the set of real numbers and n is the dimension we are working in. A finite dimensional Euclidean space is a type of Banach space that we just learned about. An infinite dimensional Euclidean space yields what we call a Hilbert space, which is critical to the study of quantum theory. In this series, however, we will only be concerned with finite dimensional Euclidean spaces with a maximum dimension of 3. Let's consider 3 of them now. So R1 turns out to just be the real number line itself that we all used in elementary school. R2 is the Euclidean plane itself. So if you use Cartesian XY planes, you've used the R2 all along. And then you have R3. This is the three-dimensional space we will be working in within the series, and it's known as the fundamental physical space of geometry. So using Cartesian coordinates, that would be the X, Y, and Z geometric space. Finally, let's consider manifolds. We will consider the notion of manifolds, which will complete our necessary introduction to mathematical spaces for this series and will finish out this episode. A manifold is any space that is yielded such that the local structure is that of a Euclidean space. Consider, for example, a basic sphere in 3D. A sphere, as we know, is obviously not flat, but if you stand on its surface, think of the Earth, for example, you don't look at large distances, it looks pretty much flat. So the line element of that region is then yielded by a Euclidean metric, with components given by what's called the Kronecker delta function, something I have covered extensively in a prior video. So delta sub mu nu is equal to 1 if mu is equal to nu, and 0 otherwise. We will look more into this Euclidean metric tensor, as it's called, later in our series. So a manifold is just a topological space that locally resembles a Euclidean space in the neighborhood of each element within the topological space. For R3, this Euclidean metric yields the 3x3 identity matrix. So delta mu nu equals this 3x3 identity matrix where 1s are down the diagonal and 0 elsewhere. This gives us the components of the Kronecker delta function, or otherwise known as the Euclidean metric tensor. Any Euclidean space is flat, and each compose an example of what's called a Lie group. A group is any set that features an inverse for each element, as well as an operation that is associative that likewise features an identity element. A Lie group, then, is any group that is also a continuous manifold. And just like that, we realize that the real number line, Euclidean plane, and 3D Euclidean space are examples of Lie groups. While Lie groups as a whole are commonly viewed as being a part of advanced mathematics, we really have been working with them all along throughout our journey in typical mathematics. The goal of this series, then, is to convince you that much the same is true of tensor calculus, and we'll simply be reformulating what we already know, except under a superior language that generalizes to the more advanced mathematics. In the wise words of Lillian Rosenoff-Lieber, tensors are the facts of the universe. Thank you for joining me in this video. I look forward to seeing you in the next one. And as always, if you have any questions, reach out to me in the comments.